So we are Team 2011, and we are working with ISO New England to create a model bullet verification system. Next slide. So for a little bit of background, at ISO New England, there are bulk power systems known as BPS that are needed to be accurately represented by the power system dynamic model. Doing this is to help predict system behavior during faults and help prepare for reacting to faults. Next slide. The current system in place at the company that is being used to do that is called the Automatic Power Plant Model Verification Tool, APPMV. This tool runs 24/7, and to start off this tool, certain events get triggered, and then the tool verifies the event, runs the PPMV, and sends out the results in an email, which are quantitative. Next slide. The problem at hand is that the data isn't easily read, and also the comparisons between the power system dynamic models and the bulk power systems are only qualitative, and we need them to be quantitative. The engineers receive only graphs, cannot do chronological comparisons for a single plant, and the data is not well organized. And also, there is no way to rank the models. Next slide. So a few requirements to complete this project is that we need to determine a readable at-a-glance metrics, and we need to be able to manage, analyze, and quantify the results automatically. And also, we need to find a way to score and rank the models. And in doing so, we need to find ways to highlight the bad models, provide automatic ranking from quantitative comparisons, and we also discussed alternative scoring methods, including the signal similarity metric and the normalized root mean square error.
So the solution that we came up with is to divide the project into two parts. So there's an ECE team and a CSE team. So the ECE team is focused on designing and implementing the analysis engine, while the CSE team develops the database and the web app. So the analysis engine is being implemented in MATLAB. It's supposed to provide quantitative results, and it outputs two easy-to-read scores. The NRMSE, which is the normalized root mean square error, is the overall fit of the model, while the signal similarity is a component-wise breakdown of two signals.
The analysis engine initially uses the NRMSE as a coarse filter here. So because it is the overall fit, we use it to screen models to meet some minimum threshold. In our case, we chose it arbitrarily to be 70%. Here we can see an example graph of two signals that have a 90.63% match. If it passes this filtering, we'll then move it to the signal similarity algorithm that was proposed by two professors from Washington State University. The signal similarity algorithm scores components based on the signal's component parts, including correlation, magnitude, and phasing. Here we can see an example of what these components look like. Starting from a base signal on the left, you can see that variations in magnitude are in orange on the top, and variations in phase angle are in orange on the bottom. This signal shows a combination of variations in both magnitude and phase angle, and the signal similarity algorithm outputs these three numbers for correlation, magnitude, and angle respectively in order to generate an overall score for how accurate this model represents the base signal.
So the constraints that this project is held to is confidentiality. So we're using sensitive data provided from ISO New England, and that required a non-disclosure for all of us to sign. So all the examples that we've shown in this presentation are just test cases for our testing. So we're provided limited data sets from ISO New England to test our functions. Additionally, COVID-19 restricted us to virtual meetings, and since we are using software for this project, overall it hasn't had a huge impact on us. So adapting to COVID-19, we've been having WebEx meetings weekly with the whole team, both ECE, CSE, and the sponsors, where we present our current work and we're determining any new directions if applicable.